webcast this morning for InSpec. Let me introduce our hosts and presenters. Eric Novak, PhD of 4D Technology. He is Director of New Product Development. Kramer Lindell, Applications Engineer for 4D InSpec. And Gwendal GIRARD-SUARD from Tree Optics, who is helping us put this together and is a welcome member of the panel. Now I'm going to hand it over to Eric, but because this is a small audience, we will have an opportunity to have a conversation with you, and we trust that that Gwendal will help facilitate that. So if I may first pass the torch to Gwendal, so that you can do your introduction. Gwendal, you are self-muted, but you can start anytime.
Bonjour à tous, Gwendal GIRARD-SUARD, vous me connaissez pour la plupart d'entre vous. Je fais une petite introduction en français. Comme l'a dit Edgar, donc déjà merci à tous d'être là. Comme l'a dit Edgar, on n'est pas très nombreux, donc on en profitera pour pouvoir faire des échanges questions-réponses si vous avez des questions, principalement après la présentation. La présentation d'aujourd'hui, elle va être principalement dédiée à l'InSpec et au nouveau module Edge Break qui permet donc de faire des mesures de chanfrein, de congé et d'angle. Mais si vous avez des questions d'ordre plus général ou plus spécifique sur l'InSpec, n'hésitez pas à les poser, ce sera avec plaisir. Thank you, Edgar. I'll let you talk, or Eric.
Yeah, this is Eric Novak. I'm the Director of Business Development and the Technical Product Manager for our industrial product line from 4D Technology. And I'll be joined here from 4D today by Kramer Lindell, who you'll see in a little bit, who will be doing live measurements and demonstrations of some of the concepts I'll briefly introduce in a PowerPoint. One thing, please note, we want feedback from you, so along the way, please feel free to type questions into the questions box or the chat window, and we will try and answer them as we go, so that we can make this more interactive. And when we're doing the demonstrations, we're happy if you want to see more of something or different parts or things like that, please let us know. We want this to be valuable to everybody here. So with that, I'll get started. And again, I'll try not to talk too long because really I think the best is the interaction with the actual system so that you can see what it can do. But just by way of introduction, why are we talking about shop floor metrology? It's essentially because that will save money. According to Quality Digest, poor quality control costs companies more than $2 million a year. And the National Institute of Standards here in the US has performed numerous studies showing the value of adding good metrology to production is nearly 50-to-1 in terms of payback. And so, having the right tools at your disposal is extremely important to increase yield, decrease throughput, and save costs. So what are those costs? They fall into two main categories. One is internal failure costs, so the cost of waste, scrap, rework, failure analysis, etc., that all will slow down production, will create problems internally. But probably the more severe costs are what they call external failure costs. And those are ones associated with field failures. So having to do repairs and service of parts under warranty, handling customer complaints or failure of customers to accept parts, travel and return time and meetings associated with discussions of failures, and ultimately maybe the most important, which is customer perception, where, if you get a bad reputation or fail to handle issues in a timely manner, that can have long-term business consequences. And one of the challenges in aviation is, inspection and metrology is really critical. Almost every inspector out there, if there's any doubt whether a part should pass or fail, he will always reject it or put it in the rework bin, because the cost of failure is simply too high. I've heard many times from our customers and from inspectors that they think about every engine they work on and every piece of an aircraft and think, what if my mother got on that aircraft and it needs to be safe? And so that actually leads to aviation having among the highest failure rates of any precision machining industry. And traditional techniques are just no longer sufficient to control quality. So, surprisingly, there's still a large number of calibrated eyeballs and fingernails out there that are doing measurements, essentially with one person and their judgment, but they are operator dependent and, of course, non-quantitative, non-gauge capable results. The next level of sophistication, and this is probably more common now than anything, is to use replication and then either a 2D profiler or an optical comparator to look at a cross section of a given defect or part. The replication material is expensive. It's a time-consuming method because the replication material has to dry, be scribed, go to another instrument. But more importantly, it still lacks a lot of quantification. Did you really get the deepest part of the pit? Did the material really penetrate all of the way? And so these are very subjective, non-gauge capable methods. On the other end of the spectrum are lab-based measurement systems. And that might be something like a 3D microscope or a high-quality stylus system. But these systems are expensive. They can't handle large aviation parts. So again, you're often relegated to needing replication. They're difficult to use many times. And if they're in a metrology lab, that lab generally is quite busy. And it may be days before quantitative measurements come back to the shop floor. And so our goal, and we've been working, with the various people in aviation, and actually partnered in the development of this product line with General Electric, Rolls-Royce, Pratt, and others, is to bring accurate 3D surface measurements to the part on the shop floor and make quantifying a defect just as easy as taking a picture with a cell phone or a mobile. So here you can see some different examples of that. Being an optical technique, you can actually use fold mirrors, as you see in the center of the field of view, to look inside fir tree roots. You can measure large cowlings. You can measure inside pipes or outside shafts. Wherever the metrology needs to go, if you have a handheld system of sufficient resolution, now suddenly you're able to dispose of parts instantly. Operators can have perfect confidence in the results, and so they can pass parts all the way up to the specification, and the overall operation becomes much more efficient. Talk briefly about specifications that we came up with. We currently have two models of our handheld surface gauge. One is the standard 4D inspec with an 8mm by 8mm field of view, 2.5 millimeters vertical range, and 3 micrometers vertical resolution. The standoff distance from a part is fixed, so the instrument will always be 35 millimeters away, or the instrument, if you use a fold mirror, that combined distance between the instrument and the part will still be 35 millimeters. The XL has nearly twice the field of view, but more than 3 times the vertical range, and just about twice the vertical resolution. So here we're talking about 8 micrometers vertical resolution, standoff distance considerably larger, but still very tight lateral sampling for both instruments. So more than sufficient to be able to quantify defects which are, visually or tactily observable. And in addition to being strictly handheld, being a small unit, you can actually configure it in a variety of ways. So it can be on a benchtop workstation with a flexible arm, so you can hold it at various orientations with respect to the part under test. This would be very good for new make shops if you're doing the same measurements over and over again. The most common configuration would be on a portable stand that will hold the instrument, the computer, and a power supply so it can roll around the shop floor and go wherever measurements are needed. And this is by far the most common configuration these systems come with, again, taking advantage of the portability of the overall system. And then you can go all the way to on-wing applications. So the system can come with a holster, like you see on the right, is such as you can clip to your belt, and the entire system then can be placed in a backpack with a small power supply that will power it for more than 8 hours. You can have a mirror kit in there, and then the instrument itself will run on a ruggedized Microsoft Surface Pro running Windows 10, 64-bit, and you can take metrology wherever it needs to go very simply, and upstairs into into aircraft. Even the marine people will bring this into submarines and things. And then if you're going between sites, there's another version that comes in a full travel case that makes it very easy to travel between facilities. And then last but not least, the system is very amenable to automation. Because it is vibration immune 3D measurements, it can be mounted on a robot, as you see here, taking various measurements on an automotive part. And we have native support within our software for the universal robots, and then also support via command interface structure, a remote access software that you can use any third-party program to control our system. So if you have your own automation, this will integrate within your factory. An optical system is extremely insensitive to material shapes, material finishes, and material types. So our system is in use measuring carbon fiber, fiberglass and composites, plastics, metals, and anything from very rough rubber all the way to ultra finished blades. So it really, the large dynamic range of cameras allows measurement of most any surface without any preparation. Now you do have to bring dirt and debris off the surface because we are measuring what we see. And so if there's, a piece of dirt, we would measure that as a high point. And then in terms of aviation applications, it's everything from seals, turbine blades and blisks, bearings and bearing races, actual turbine blades, shafts, and then looking at everything from corrosion to rivet and fastener depth, edge break and chamfer, blend height and radius for repaired parts. And we'll give you examples of various of these later. Weld joints to look for cracking and look for the seam height. And then, further examples, measuring, again, almost any part, from wear scars on hydraulic and vacuum lines to measuring critical portions of gearboxes and fir tree roots. Now I'm just going to go over very briefly a few quick applications, and then we'll turn it over to Kramer to actually do some measurements and hopefully have you guys ask further questions about system use. So, obviously a big application is corrosion pitting. The advantage of three-dimensional metrology is you can quantify all of the pits within the measurement field of view simultaneously. So in the middle, we have a false color height map where blue is low and red is high. So you see a lot of blue pits. In the upper right, we've identified every pit that is deeper than 25 micrometers deep. And down beneath, we have a CSV exportable table that will give feature height, area, volume, percent coverage by corrosion, distance to neighbors, and density. All of those things are automatically calculated with no operator intervention. For scratches, no need to guess where the deepest portion of a scratch is. Again, we identify the entire scratch length, and in this case, it's 22 thousandths of an inch, or about 50 micrometers deep at its deepest point. And then with edge break and chamfers. So these radii are critical in aviation. They can affect performance, they can affect cracking and longevity. And we have the capability using 3D of making measurements which are insensitive to the orientation of the part with respect to the instrument. So if your measurement instrument, if your system is twisted or tilted with respect to the part, we can actually tilt more than 15 degrees in any direction and maintain accuracy to within 1%. And that's really the advantage of three-dimensional metrology as opposed to a 2D trace, which is extremely sensitive to how it's oriented on the part due to cosine errors. Rivet depth, planarity, perpendicularity, all automatically calculated with the system. Part marking is a big application. If part marks are too deep, they can initiate cracking or corrosion. If they're too shallow, you can lose the serialization of parts and not be able to track them through their life cycle. So again, we'll find the entire feature, and in the right, you can see a dot peen. Each and every dot is identified. And again, the depths, volumes, areas are all calculated automatically. 3D parts can be sintered metal, as we see here, or plastic. Again, you can look for voids. You can look at surface roughness and other S parameters, which are three-dimensional surface parameters on those. Cooling hole geometries, if you need to know the angles, the volume of the cooling hole well, that can all be calculated. And the upshot is, with simple 3D metrology, you really get an extremely rapid return on the investment in the measurement system. These are real-world examples from aviation, where we've been told that at one factory, rework rates went down by 30% on one of their most critical components because they were able to pass parts that they used to err on the side of caution and fail. Obviously, reducing measurement time on pitting is a huge benefit. To be able to quantify more than 100 corrosion pits in a single 1 second of measurement. Yields typically have gone up, and this has been surprising both to us and some customers. A lot of people worry that more metrology means more failure. But in aviation, they're already failing parts if they're unsure whether they're good or not. So allowing an operator confidence that he can pass a part when he measures something that's 20 micrometers and the specification is 25 micrometers, he used to have to fail that because the eye can't tell that difference. But having a certified ISO qualified gauge allows you that capability. And then again, reducing labor and measurement time through being able to do measurements on wing without disassembly is a big issue. So this is my last slide, and then we'll turn it over to Kramer to do some further introduction to what the system looks like and how it operates. But the goal of this instrumentation is easy handheld measurements wherever you need them. And the system is robust. It is immune to dust. It can even handle light water spray. It is frequently dropped by customers with no ill effects. It can access small spaces, and you can use mirrors to look sideways and get into even smaller things like bolt holes. And it's really designed for use in real world applications for an average person. It does not need a sophisticated operator. Usually our customers are taking measurements within 10 minutes of us arriving on site and starting up the system. So with that, I'll turn it over to Kramer, and again, please feel free to type questions along the way.
All right, I'll go ahead and share my screen here so I can share my camera with all of you. Able to pass it over, Eric. There we go. Okay. All right, here's my my camera to show you guys my setup. This is the 4D Inspec. I have it right now currently in a desktop configuration. This allows you to put it in a microscope stand here, adjust for focus there. Allows you to put different parts underneath the Inspec, but really the real power of this instrument is the handheld 3D measurements. To do that, we use this LED right here that is polarized in a special way that allows us to take measurements instantaneously. That allows us to get 3D measurements. To take a measurement, we can just click this button right here on the top of the Inspec whenever we are in focus. And to get in focus, we use this while we're in handheld mode here. Use a focus aid. You can put right here in the front of this this instrument. It slides right in there. That allows me to get to the right focal length on any part I put this on. So I can put it right here, take a measurement. Whenever I'm in focus, I can click this button and take that measurement. So I can start with a basic measurement on a flat surface of some part marking. To do that, I just need to put the Inspec down, get to the right focus, click this button whenever I'm ready, and I'll be able to get a 3D surface map of whatever this LED reflects off of. So this LED comes down through some lenses here, reflects off a surface, back to the camera, and be able to put together a 3D surface map of the surface it's reflecting off of. So go ahead and go to my 4D software here, and right here you can see my live video. This is what the camera is seeing. And right now it's blurry, out of focus, and gray. So I can get that into focus. And once it's in focus, it turns green. That's how you know it's we're having a strong signal there. So like, there we go. We have an auto brightness feature that allows us to get to the correct brightness quickly. Any red pixels means they are overexposed. The auto brightness takes them away. So right there we have a green live video. That means we're good to go. We can click that button I was showing you guys, take a measurement pretty simply, and that gives us a 3D surface map of our surface there. So there's a few different ways to view this measurement. If we look at a 3D map, if we wanted to, right here, right, this is a traces view. Here's the 3D surface map to give you a nice little view of it. A real powerful tool we have is that feature analysis that Eric had touched on. We can go ahead and look at any depths that are deeper than 1/1000th of an inch. So each one of these features is showing up is deeper than 1/1000th of an inch. Each pit is being flagged as a feature, and every statistic you want to know about it is being called out right here. We have a weighted height, area, volume, length, width. Anything you want to know about each one of these features is being individually and simultaneously analyzed to make everything within this field of view a nice, quick, and easy analysis. We have some shape removals. I can show you what the difference would be for different shape removals. So here I was using a tilt removal, which is essentially just removing the tilt I had to the inspec. We were pretty forgiving with how you can be tilted. You don't have to be perfectly orthogonal to the part. This is a handheld, so it's made to be pretty easy to use. So I can remove the tilt. This is what it would look like if I hadn't removed the tilt on my shape removals. So you can see I was a little closer on the top here. This prevents me from being able to get these defects to stand out amongst the tilt. So using that shape removal of tilt helps these defects stand out. We have different, you can take measurements on curved parts as well. Different geometries don't bother us too much. This is a curved blade. You can see I have a defect here circled with a Sharpie, a little marker right there. I can take a measurement on that the same way I would take a measurement on that flat surface. I would take this inspec, put up to the part, let that blue LED reflect off of that area of interest right there. And when I'm ready, I'll take this, click this button to take that measurement. So I can go back to my 4D software and show you what I'm seeing. I'll go back to my live video here, and I'll go ahead and get the auto brightness a little higher. So there's my defect right in the middle there. I can go ahead and click that button, take that measurement, and we can look at that in 3D. So here's my surface of you can see what I took a measurement of there. This is my 3D surface. I could go ahead and remove any shape that surface has. So I can remove the curvature of the part without removing the curvature of the defect. Flatten this out so that I can analyze this with our feature analysis. So this part will flatten out here as I recalculate. You're able to recalculate previous measurements here in the stack with different settings. So I changed the setting from tilt to variable shape removal. That shape removal removes the shape of the part without removing the shape of the defect. That allows me to be able to put this into the feature analysis that we were using, and that defect on this curved blade is analyzed for you. You don't have to guess with the 3D data where exactly the deepest part of this defect is. It'll tell you. It could tell you exactly the point that is the deepest. You can see it's right here towards this upper left-hand side of that defect. And everything about this defect is quickly given to you in this feature analysis. So you can quickly measure that. You can just put that inspec up to the part, measure it, and you quickly have these results. The idea is that you can take this inspec to the part, take that measurement, and get defect analysis results very quickly and easily. You can go ahead and show you guys different ways to measure on different geometries. So right now we are using this focus aid that allows us to put up this inspec two different parts, whether it's flat, whether it's curved like this. This is more universal focus aid, but we have different ones that allow us to do different types of measurements. This is more of a V groove as opposed to this rubber tip. This allows us to ride along edges of blades. We can put that into the end of the inspec here. The same way this one works, and we can look for defects along a blade edge. So if I wanted to look at this this blade edge here, I can put this V groove focal aid right here and search along this blade edge for any defects. So if I can go back to my live video, and whenever I'm ready, I can just go ahead and click this button again whenever I see that defect in my field of view. I'll go back to my live video and take a measurement when I get a defect in the field of view there. So you can see I'm focused there, and those red pixels are overexposed. So I'll bring that brightness down a little bit, and I'll go and take a measurement. I'll purposely be a little bit off of vertical. We have some new cropping. It allows us to be away from vertical, and we can crop that in any way we want.
Yeah, we did have a question regarding
Yes.
that, Kramer. So
Okay, yes, perfect. So calculate that. So I will go ahead and crop this with our new cropping right here. So I'm a little askew from vertical, so I can move my crop in the advanced cropping. I can adjust this to go along the axis of the blade edge right there. I can.
it might be a little more obvious if you show them the surface there.
Yeah. Okay. You can do it with the live video. It's a little dark to see on this measurement, but you can see the general direction on the surface data here. I'm going along the axis of the blade edge there. I'll recalculate that surface with this new crop in the advanced cropping here. And I'll get this nice edge of the blade right there. Now I can draw my own trace. I can analyze this with in this traces view. I can draw my own trace across here, like so. And I can move this trace around until I find the deepest part, which is more towards this left side. And when I have that, I can drag over from this left side some highlights, some calipers, and I can see the width of this, about 28 thousandths of an inch, and I get a peak to valley, which would be the highest to the lowest point, the difference of those 2 points. So I'm about a 4 thou, almost 5 thou deep on this pit. So blade edge nicks can be analyzed with this traces analysis. We don't have to be vertical like we used to be with our measurement. Alignment doesn't matter because this new advanced cropping mask, it can be rotated in any direction you want it to be. You can rotate it so that we don't have to be exactly perfect up and down when you're aligning your measurement. So that's a nice little tool that's new to us and pretty useful in this case. All right. So we can get into a little bit into what some new things we are doing. Right now we're being used for the that defect analysis that I've been showing you, and we are starting to do a little bit of this edge break analysis. So for edge break testing, we made this edge break standard. I can get you a little bit a better close up probably in this this page right here. And so this is the edge break standard here. Right here on this side is a chamfer. That's what's currently being measured by the inspec. It's just a broken edge that has a machine flat right here. So we have 3 planes, and the inspec is measuring perpendicular to the chamfer face so that it can get data off all 3 of these planes. That allows us to identify what plane belongs where, and we can reconstruct the material that has been removed. On this edge, we have a rounded edge that kind of works a similar way. We can identify the 2 planes that are adjacent to this curved area, and I can take some measurements off both of these and show you how our edge break analysis works. So I'll go ahead and put our universal focus aid back in and take some measurements on this this edge break standard. So again, I'm just going to put up the inspect to the part. Everything this LED reflects off of, we can get a 3D surface map of. So we'll get a 3D surface map of this edge break geometry right here, and our analysis software can reconstruct the edge and tell us all the data we want to know about this chamfer. So back to our 4D software here. I'll get this in focus, put the auto brightness on, and get that to where I want it to be, which is about right there. I'll go ahead and take a measurement once I get the correct shape removal on. All right, so there's our chamfer right there. We have our left side right here, our right side right here, and our chamfer face. So the chamfer, or our software is going to do is identify the data points that belong to this left plane, this chamfer face, and this right plane right here. And so this right side is certified to 40,000ths of an inch. This left length is certified to 40,000ths of an inch as well. And we expect this chamfer length to be about 56 thousandths, like it's shown right here. So these blue data points are being identified as belonging to this left plane. Red points are being identified as this right plane, and the pink ones are being identified as that chamfer face. With that 3D data, we're able to remove any of that tilt. You can see I wasn't perfectly, this top side is a little closer to the end spec than this bottom side. You can see I'm a little bit off center, a little askew on my alignment there. I didn't do a perfect job, but that 3D data, it doesn't have to be perfect with the alignment. So the 3D data can remove any tilt and get you some accurate chamfer results. So these there are a lot of results here. It might be easy to refer to this diagram. So we're displaying this chamfer length, which is what's commonly measured, sometimes with 2D measurements. We're reconstructing this right length where these two planes would intersect. This is what that right length would be. Same with the left length. And then there's a bunch of angles in between that we are displaying as well. So I could do something similar for a rounded edge. The other side of this standard has rounded edges. I can go ahead and take a measurement the same way I would for the chamfer. I can go ahead and put the LED on that side, click that button when I'm in focus. Go back to my live video here and get a good measurement of that rounded edge. All right. All right, so there's my rounded edge. So the software is going to identify the data points that belong to this left plane, data points that belong to that right plane, identify where that plane stops, and tell you where that curved area in between is. That's what this pink banding is. And fit a best fit circle to that. This is certified to 40,000ths of an inch, so you can see we're getting just about that. And again, we are getting telling you a lot more about the rounded edge as well. We're telling you this right length as well, this left length. This is the radius, the edge break radius of that best fit circle. The different inner surface angles, arc angles, everything you would want to know about this rounded edge. We're displaying for you here, and each one of these parameters can be set as a pass-fail parameter. So you can, if you had a certain spec, so you had say something like that, it would show up green. You can make it fail. I can make it fail for you if you want to see what that looks like. And that would fail for you. So you can set up, if you have certain specs for each of these, you can set those up as pass-fail parameters, and it would flag each one that passes, each one that fails, to make things easy during analysis. So it makes these edge break.
We're often asked,
yes,
is the range of capability of the system. So we about the smallest edge break radius that we've seen specified is 75 micrometers, and we're fully capable there. And then we can actually measure edge break radii up to many millimeters in radius as well. So.
All right. So we can also take a measurement on just a cylinder. That's the last part of our edge break analysis software. Makes things easy on for measuring radiuses of cylinders. Back to my live video, take a measurement on a cylinder real quick. And I'll get a nice measurement of the cylinder. There we go. And this will be using the same concept as the others. This will allow us to, there's my cylinder, put that in the 3D radius of curvature. And this will give you just a simple output of what that radius is right here. It's about what we would expect. That's what we get for this cylinder. And you can also, in traces, highlight, I'll get rid of this, highlight the radius and get the radius of curvature right here. So there's a couple ways to find your radius of curvature if you're interested in finding that on any parts you're looking for. So and in addition to defect analysis, we can also measure small geometries like edge break and so chamfer rounded edges and radiuses of cylinders. So I have a few parts here. I can show you some different measurements. We can go through some calibration. We can do some measurements with a fold mirror. This allows you to get in between different, say we want to get inside these blades, we can do that. I can kind of open it up for any requests. We have a few different parts here. But I'll go ahead and I can go ahead and do a quick calibration. Everyone likes to see the calibration process, which is fairly simple, fairly quick. So I'll go ahead and do that in the meantime.
Yeah, and while you get set up, as Kramer said, we have about 15 minutes here left in the presentation for folks. So I know we have a mix of current users at Safran, as well as some groups that have interest in getting a system. So if there's specific questions you have, again regarding how you've been using the system or what you'd like to see, please let us know, and we'll try and customize the remainder of the time to what best suits you.
All right, so the calibration process is really just setting this standard down onto the microscope stand, getting it into focus, just moving this up and down until the it's green. So right there, I'll be out of focus. I move that back down. I'll get into focus. I open the calibration screen, which is just in settings. And then I can align that these ridges to the red overlay. And then I can go ahead and just take a measurement, and it will compare it, the heights that it measures to that certified height. It displays what the certified height is and what I'm measuring and my percent errors versus that. And it'll just tell me that my calibration is verified, ensures that I'm measuring correct depths in correct places. And every time I calibrate this instrument, it goes into a calibration log. And I can look at the record of every time this instrument was calibrated and what those measured heights were and over time. So it's a very simple process. Takes me about 30 seconds. Pretty simple, pretty easy to do. We can look at the 3D measurement just to get a better understanding of the surface map that it's putting out. So that surface of that calibration standard.
Hey, Kramer.
Yes, sir.
I had heard you guys talk about the auto brightness changes, and this is actually the first time I've seen that
Oh, okay, yes.
working. Could you talk about how that works and also the effect usefulness versus?
Yeah, absolutely. I'll go ahead and go to a sample that has a kind of a dark rubber and a bright metallic surface. I'll go ahead and pull this back out. Put my standard away real quick. Back in this safe box. But I'll go ahead and take some measurements on this dark and bright sample. Go back to my. So I'm just going to go back and forth between this dark spot and this bright spot. So this is very reflective, very bright, gives the camera back a lot of light. And this is very absorbent to light. It doesn't give back a whole lot to the camera. And the auto brightness will be able to adjust the exposure time on both of these samples very quickly. And we can go and see what that looks like. I'll get in focus first, like so. Okay. And just to show you how I'm getting that in focus, I am just moving this. This is adjustable. I can pull this in and out. And once I'm at the right focal distance, I can put that down anywhere. It's going to be in focus. And then I can go back to my software there. So here is my auto brightness is working. I can move it to the bright spot, and very quickly, like you can't even really tell that I moved to the metallic surface there. But then I can move back. The auto brightness moves, and then back to the metallic surface. And before you would have to, when you go back from the black surface, before you'd have to wait maybe, I don't know, 10 to 20 seconds for the field of view not to be completely red. But it's almost instantaneous now. You can barely, I'll try to make it fail, but I can't. But yeah, it's a good new feature we have. Pretty instantaneous, that exposure time being adjusted in real time.
And one of the other things for existing users, it used to be that there were some samples that were simply too bright for the instrument, and so you would have to really struggle to measure. The new auto brightness changes not just gain on the camera, but exposure time, so that we have a much larger dynamic range. Essentially, there shouldn't be a part anymore that's too bright for the instrument to measure.
Reminds me the option looks highest points.
So you're breaking up for me there, Edgar.
Sorry, this part reminded me the plot options
Yes.
for selecting the highest points.
In the feature analysis.
Yeah, in the feature analysis, yeah. Yeah, that new addition. So go back and move this out of the way real quick. So before we would be going on the centroid point, for every feature. Now we have that option I kind of touched on earlier, but that we can go to the max height. So in the feature, yeah, right here, we can go to the centroid point to the absolute deepest point in this case of every feature. So this point right here is the deepest point on this in this kind of trough right here.
And so that's used a lot when people are measuring scratches or larger pits and things and trying to identify how far from an edge the deepest point is.
Yep.
All right. Are there further questions from the audience? Things you would like to see us measure before we sign off? And again, we're happy not just to have the webinar. But if you'd like, an individual call with Gwendal or with Gwendal in the factory, he has a system. We obviously have systems. We're happy to work with you on any questions or talk about further applications.
Thank you all for waiting. You're done. It is very early in the but I wish you all a good afternoon. Did you have?
Yeah, I don't see further questions, and yeah, Edgar, you are breaking up a little bit still. So yeah, again, everyone, thank you for your attendance, and let us know how we can help. Again, the products we want, to have our key aviation customers be partners with us moving forward. So if there's analyses you'd like to see, additions, essentially the features you see that just got added to the software here, that we demonstrated were all from customer feedback. So please let us know how we can serve you better. And with that, we'll sign off, and hope you all stay safe and have a good holiday season.
Thank you
Thank
for
you
your
very
time.
much. Thank you, Eric.
Thank you.